Okay, any questions on this? The electric motors, etc.?
Can I ask a question different from electric motors?
Sure, go ahead.
I am getting confused about the definition of dipole magnetism. So basically everything that has a magnetic field has a magnetic dipole.
Now, every current that goes around an area has a magnetic dipole moment.
So for the magnetic dipole moment to exist, there should be a current.
Yes.
So magnet bars don't have magnetic dipole.
We will come to that later on. I mean, they have kind of what we call an effective current because they're made up of electrons. Well, if we imagine electrons as rotating spheres, they have current. So we will come to that later on. Other questions? Now let's go back to, let's review the circular motion. Now we said that if we have a region of space which has a uniform magnetic field, and you just send some charge through this region with an initial velocity, and let's say it's a positive charge, there will be a magnetic force in the upward direction, and the trajectory, it will be always perpendicular to the velocity of this charge. And we said that it will be doing uniform circular motion, and this will be its trajectory with some radius r. And to determine the relation between the magnetic field, its speed, and r, we know that the centripetal force is caused by the magnetic force, which is qvb. And if our object is doing some uniform circular motion, the central force has to be equal to v squared over r. Or canceling the v's, qb should be equal to mv over r. So if you know, let's say, the charge, the magnetic field, the radius, you can determine the velocity, the speed of the object. Or if you know the speed, the magnetic field, and the radius of the orbit, you can determine the ratio of the charge to the mass. Now, what about its period? Period of rotation. Now, the period we define as the time it takes to complete one full rotation. In one full rotation, the distance that the object covers is just 2 pi r. Its speed is v. So this is equal to 2 pi times r over v. But you see, from this relation, r over v is nothing but m over qb. So r over v, I just moved r and v to the other side, q times v to this side. So this is the period of the rotation. Well, you see, it is independent of how fast or slow my object is moving. That's kind of nice. So whatever its speed, its period of rotation will be exactly the same.
So it only depends on what?
On the mass, on the charge, and on the magnetic field. Well, this is basically one phenomena that we use to build accelerators. Now, to accelerate charges, we know that we need to apply some potential difference, some electric field that will be changing the velocity. Magnetic field doesn't change the speed. It changes the velocity, but not the speed. So we cannot change the energy of a particle only by using the magnetic field, but using electric field, we can accelerate charges. So let's assume that we have a parallel plate. We create a parallel plate, one of them positively charged, the other one negatively charged, let's say initially. And we also put a magnetic field in this region. B is into the screen. Now let's imagine a proton somewhere over here. Which direction it will accelerate? So this will be the acceleration of the proton. So if you start from here, it reaches over here. It's moving in this direction, but now it's in a region where there is a magnetic field. What will be the direction of the magnetic force acting on the proton? It will be upward, so it will just curve upward. Now there is a problem. If you send the proton from here with this polarization of the capacitor, positive charges over here, negative charges over here, the electric field here will try to slow it down. So it will just stop midway. What we have to do is we have to change the polarity. So during the time that the electron starts from here and reaches here, before it reaches this point, we have to change the plus and the minus signs. If we do that, when we reach over here, the proton will accelerate again. So it will just accelerate, so it will be moving faster. Now we came over here with a larger speed. If the speed is larger, to satisfy this relation, the radius should be larger. So it will, after that point, it will go around the circle with a larger radius. And then before this instant, we have to again switch the charges on this capacitor. If we can do that, it will just keep on accelerating. Each time it passes through this gap between these plates, it will accelerate, it will come out at a larger speed, and then it will just turn around. And before it reaches this gap again, we have to switch this again. So it will keep on accelerating until the radius is large enough for your device. So this is the region where you have the magnetic field. So you make an opening over here. So the electrons now just leave your device, and protons, you can do whatever you want. At each passing through this gap, it will be accelerating until it reaches a given speed, at which it will just leave your device. And this is one of the simple accelerators that we had. This is called the cyclotron. Now, the nice thing about this cyclotron is that the time that we have to make this switching is nothing but half the period. And the period is already fixed by the type of particle you try to accelerate, proton or electron. You know the mass, you know the charge. Well, you can determine the magnetic field, whichever magnetic field you can create. So you know the period, you know what frequency you have to use to switch this polarity. Or most of the time, you usually have already a power supply or a battery which changes its polarities at a given frequency. So you choose your magnetic field to match that frequency, and you have your accelerator.
How do we switch the polarity?
Well, for example, this power that the city electricity, it changes 50 times a second. Now we will see it's easier to generate electricity with switches, which makes this switch, than to generate a source like a battery. Now this works up to energy, let's say 50 MeV. For proton. Well, basically what happens is once the proton reaches 50 MeV, its speed is already very close to the speed of light. If it is moving at the speed of light, these relationships we cannot really use. And the period of oscillation, this period of oscillation, the switching, it changes based on the energy. So we cannot use a fixed frequency. That is one problem. Furthermore, the radius becomes very large. That's another issue. So for such systems, if you want to go even at energies higher than this, what we create is what's called the synchrotron. It basically adjusts the magnetic field. The magnetic field will not be constant. So what we do, for example, in LHC, the ring is already fixed. LHC is a synchrotron. The radius is already fixed. So you increase the magnetic field as the protons are accelerating. So the more energetic they become, the larger the magnetic field that you apply. So you have to synchronize them. So that's where the name drives. You have to synchronize the change in the magnetic field with the change in the energy of your particle. And with these devices, we can go quite high at high energies. Just the background knowledge. Okay, any questions? Now, if not, I will be starting the subject of how do we create the magnetic field, which most of you seems to be quite curious about. So let's, question? Okay, so the basic idea is that, okay, the fact that we are using to create a motor is this expression over here. That the torque is given by this expression, which tells us that the torque will try to rotate the magnetic dipole moment in the direction of the magnetic field. When they are in the same direction, there won't be any torque. Of course, when they are exactly in opposite directions, there won't be any torque either, but that is not a stable point. The moment that you just rotate it slightly, the magnetic dipole moment will try to align with the magnetic field. Then the trick is, what if the magnetic dipole moment is not fixed? So it constantly flips its direction. So let's say this is the direction of the magnetic dipole moment. This is the direction of the magnetic field. Let's say in this direction is my magnetic dipole moment, magnetic field in that direction. So if we start like this, it will try to align with the magnetic dipole moment, magnetic field. At this instant, we just switch the direction of the current. If we switch the direction of the current, the magnetic dipole moment, its direction changes. Well, it still tries to align with the magnetic field. Again, we switch the direction of the current. It still tries to align with the magnetic field. And so it keeps rotating as long as you keep switching the direction of the current. So what will happen if you keep the magnetic dipole moment constant? Let's say you reach here. Now this object has a mass. It has an inertia. It will keep rotating. But when we are here, the torque acting on it will try to rotate it in the other direction. So you started from here. It has an angular acceleration. So its angular speed will increase until you reach this point. After this point, the angular acceleration will be in the opposite direction as the angular velocity. So its speed will become slower and slower. Its angular speed will get smaller and smaller. After at some point, it will just stop, and then it will rotate. It's just like the spring, exactly like the spring. If you don't change the direction of the current, it will just oscillate back and forth. In fact, it's exactly like the pendulum. Well, you see, if you start from zero velocity over here, energy conservation tells you that it will stop. Well, this problem is exactly like the pendulum. Exactly. So if you can do something with the pendulum, you can do the same thing here. Other questions?
When we try to accelerate the charge particle, why can't we use a fixed frequency when changing the capacitor sign?
Well, we can use a fixed frequency if it is not relativistic. You see, when we have relativistic effects, this relation will not be true. Or you can say that, okay, I mean, don't tell you that I'm telling you this. The mass increases as the speed increases, so period changes. I would deduct points from you if you give such an explanation in special relativity. Other questions? Okay, so let's see what creates the magnetic field. Let's just try to apply our understanding of Newton's equations to see what creates the magnetic field. So we had seen that if there is a magnet, it creates a magnetic field. So if there is a charge over here, let's say this is the North Pole, this is the South Pole, this is the direction of the magnetic field. If there is a charge over here moving in this direction, there will be a force acting on it. What will be the direction of this force? A positive charge, let's say. So B is downward, V is in this direction, V cross B into the screen. The magnetic force acting on this charge will be into the screen. Okay, let's remember Newton's third law, action-reaction pairs. So we already, if the magnet is exerting a force Fp onto this charge, if Newton's third law is correct, then this charge should be exerting a force on the magnet. Well, we know that the magnet feels a force due to a magnetic field. So the only way that this charge will be exerting a force on the magnet will be if this charge creates a magnetic field. That's the only way it will be exerting a force. Furthermore, if the velocity of this charged particle were zero, then there won't be any force acting on this. So there shouldn't be any force acting on the magnet. So again, if the velocity is zero, the charge shouldn't be creating any magnetic field. So this basically tells us that the magnetic field should be created somehow by moving charges. And where do we have moving charges? Well, the wires, the currents. There we have moving charges. And we already know how to measure the magnetic field. We can determine measure the force acting on a charge. And so we can just determine how the magnetic field changes in a given region. So we can do experiments to try to determine what will be the magnetic field created by such a wire carrying charges. And it turns out that if you look at this point, and again, imagine a very small segment of wire here. Let's define, again, this vector dl. The length of this dl is the length of the segment that we are imagining. The direction is along the wire and in the direction of the current. Let's assume that this point is at a distance r from that segment. Then the magnetic field created by this very small segment, Well, of course, all the segments will be creating magnetic fields. So to calculate the total magnetic field at this point, we have to calculate the sum of all the contributions from different segments. And the contribution from this segment will be just mu0 over 4 pi dl cross r times I. This is called the Biot-Savart law. So this is the magnetic field. Divided by r squared. Well, in a sense, it does resemble, to some extent, the Coulomb law. You see, we have this 4 pi r squared dependence. And the charge, we said that what feels the magnetic force is not the charge itself, but the charge times its velocity. So this is like the charge times the velocity. And this is r hat. And in the Coulomb case, we had the 1 over 4 epsilon 0. Here, instead of 1 over epsilon 0, we have this mu0. And mu0 is, in suitable units, is 4 pi times 10 to the power minus 7, if I'm not wrong. Yes. It's Tesla meters per ampere. By the way, this is exact. This is not an approximate value. It's an exact value. Why don't we just cancel the 4 pi's? You will see. Well, in physics laws, you always have the conservation of the number of pi's. So if you just cancel it over here, they will appear somewhere else. Well, you see this 4 pi, if you remember the Gauss law, 4 pi r squared is the area of the surface. That's what we still would like to keep somehow. Mathematically? Sure. I mean, just define mu0 as 10 to the power minus 7, and you don't have that 4 pi over there. Well, to simplify the calculations, you insert these 4 pi's. To simplify further calculations. What is Coulomb? 1 Coulomb. We didn't really define 1 Coulomb. We will be defining ampere. The 1 Coulomb will be the charge carried by a current that is 1 ampere. We will be defining 1 ampere. But if you change the definition of ampere, that appears over here, you change the numerical value of mu0. So we define 1 ampere such that this is exact. Later on, we will see that this kind of amounts to the definition of the speed of light. If you remember our discussion of on 109, the first week, the speed of light has an exact numerical value because we define it to have that value. And using that value, we measure 1 meter. We define 1 meter. There is an uncertainty in what we mean by 1 meter, which, I mean, we have that uncertainty because we define the speed of light to be an exact number. Again, a conservation of the uncertainties, let's say. We had 2 choices. Either we would define 1 meter to be a fixed quantity, and then there will be an uncertainty in the speed of light. But speed of light is kind of universal, so we fix the value of the speed of light.
Do we have any material that fixed and just closed and stay there that equals to 1 meter?
We used to in Paris, the Institute of Standards. We still have 1 kilogram there. But then there is always a problem. For example, we still face the same, we don't have a common definition of meter that can be used everywhere. For 1 meter, we already have the definition that the 1 meter is the length of light that light travels within such and such a second. That is how we define 1 meter now. So wherever you build a laboratory, and we also have a similar definition for the second, it's just the number of oscillations for a cesium atom kept at particular conditions. So you just measure the oscillations of the light emitted by this cesium atom. And after a given amount of oscillations, you measure the distance covered by light. So you have the meter, definition of the meter. But for the kilogram, we don't have such definition. We have in Paris, there is 1 standard kilogram, and every kilogram has to be compared with that one. And that is causing us a great deal of trouble. Because now every country should have their standard meter compared with the one in Paris. So these 1 meters, I think they were created at some time, and every year or so they are being compared with the standard meter. So in Turkey, there should be 1 standard kilogram, and all the mass measuring devices should be calibrated with that 1 kilogram. And that 1 kilogram should be calibrated with the 1 kilogram in Paris. And it turns out that, okay, at some point they created these standard kilograms, all equal to the kilogram in Paris. And when they compared them again, they were different. Because there is always the evaporation, there is the humidity that adds onto your material, etc. All the things that changes the mass of an object. Now we are looking for a way of defining a kilogram in a more standard way, which will not change and every laboratory can use. We don't have such a definition yet.
Why don't they make a scale instead of kilogram?
A scale, you mean by measuring their weight? Well, one problem, for example, is the G changes from point to point. Second problem, if you want to be precise, you see, you can measure 1 meter with an arbitrary precision that you like. As the technology evolves, it will get more and more precise. But with the G, I mean, you approach the device, you are exerting a gravitational force. If you are too precise, then you will be measuring that one also. So whether you stand over here or stand over here, you will be measuring a different weight.
Why not the amount of a particular element? For example, if we take
Why not the?
certain amount of a particular element.
How do you count them?
How do we count them?
What about the isotopes? The isotopes have different masses. So we have to identify also how many of each one of isotope it has. Measurement, observation. There's no derivation for this. It's based on observation. Okay, here at least, let's just imagine historically. You are a scientist that you have strong beliefs in Newton's dynamics. You believe in Newton's laws. And you observe this phenomena that a magnet exerts a force on a moving charge. Agreed? Well, Newton's third law tells me that if a magnet exerts a force on a moving charge, then that moving charge should exert a force on the magnet. Then the question is, what is that force? Well, the only possibility is kind of a magnetic force. Well, if this moving charge is exerting a magnetic force on the magnet, then it should be creating a magnetic field. So the moving charges should be creating magnetic fields. And once you make this observation that the moving charges should be making magnetic fields, you go out and try to measure the magnetic field created by wires. Well, you wouldn't start with such a wire. You would rather make a controlled experiment using parameters that you can control. So what you would do is you would start with a straight wire. You start with a straight wire that carries a current I. and then you try to measure the magnetic field created around this wire, let's say at this point. Well, we already know how to measure the magnetic field. We know what's the force that this magnetic field exerts on. Well, making experiments with moving point charges is not so easy, so what you do is you will take a wire, a current-carrying wire, put it over here, and measure the force that that wire feels. We already know that the force that a very small segment of the wire feels will be given by I dl cross B. So if you just take some length of wire, put it over here with one orientation, measure the force, change the orientation, measure the force, again change the orientation, measure the force. You already know the current, you know the length of the wire. So if you measure the force acting on your wire by as a function of the orientation, if you make enough measurements for various orientations, you can identify both the direction and the magnitude of the magnetic field at that point. So now you know the magnetic field at that point. Well, you make similar measurements of the magnetic fields everywhere at various points, so you determine how the magnetic field changes. Magnetic field created by a straight wire changes as a function of the distance. Then, of course, you would like to go to the magnetic field created by a very small segment. You do more experiments rather than taking one straight wire like this. For example, you can take a different shaped wire with a 90-degree bend or a different angle bend. And if you make sufficiently enough measurements, you might be able to determine how this behavior. But we will rather start from that one. Let's assume that just like the F equal to ma, there's no derivation of that, but it explains our observation. Just like that, this Biot-Savart law explains our observation.
How can we this much precise about this?
Mu zero. We don't measure mu zero, we define mu zero. So that's why we can be so precise about that one. We just define mu zero to have this value. And then, of course, there will be some uncertainty in the definition of 1 ampere. What do we mean by 1 ampere? Other questions? The year 1800s. 1800s. I would say the mid-800s. That's just a wild guess. I mean, educated guess, let's say. I don't remember the exact date. I mean, it's not so easy to give an exact date because I'm sure there were hundreds of other scientists who were trying to find a similar law, who tried different laws, and this one seems to have succeeded. Well, again, let me write it over here. The magnetic field created by a very small segment of wire is given by this expression. Now let's try to calculate the magnetic field over there. We have to divide our wire into very small segments. Let me take a very small segment over here. This is my dl. This is my r for that very small segment. What is dl cross r? What's the direction of dl cross r? This is dl, this is r, this is dl cross r into the screen. Let me take another dl somewhere over here. This is the corresponding r. Now what is dl cross r? Again, this is dl, this is the r. dl cross r is again into the screen. So all the segments, the contributions of to the magnetic field from all the segments will be all into the screen. Now that is kind of nice. We don't need to worry about the directions. They're all pointing in the same direction, so we can just add the components. Let's start with this one. dB. What is the magnitude of dB? The magnetic field, the contribution to the magnetic field of this very small segment. Well, mu 0 over 4 pi r squared. I times the magnitude of dl is just dl. The magnitude of r hat is just 1. And the sine of the angle between the two. Let's just call that angle theta. This angle is theta. So the total magnetic field will be just the sum of all of those. It's just mu 0 over 4 pi r squared I times dl. Sine theta. So this is the magnitude of the total magnetic field. Well, let's see. As we change different segments, as we consider different dLs, mu 0 is constant, 4 pi is constant, I is constant, but r is changing. This r is this distance. It will be constantly changing, so it depends on our integration variable. Theta will also be changing. It will also depend on our integration variable. So I cannot take sine theta. I cannot take r squared out of the integral. The rest I will just take out. Now let me just do this boring exercise. Would you like me to go over how to evaluate this integral? It will be boring, but you should do it at least once. So how many of you want me to evaluate this integral? At least to a point, to take this integral up to a point after which you can evaluate it. Okay, don't sleep. Now let's just take, let's take our reference point. This is, let's call it, or rather than that, this is my point over here. This is my reference point. And this distance, let me just call it L.
Why do we need reference?
I mean, I will be taking some integral from some value to some other value. Let me just, if you don't want the reference point, okay, don't take the reference point. I will just take this length to be L. And this length over here is D. Now we have to choose our integration variable. So we have to choose one variable, and we have to express all the other variables in terms of that single variable. So here, L will be changing as I change this dl. R will be changing. Theta will be changing. You can choose whatever you want as your variable. Let me just choose theta as my variable. I would like to write everything in terms of this theta. Now let's start with R. R times sine theta is just D. So R is D over sine theta. So this is kind of easy. I just wrote R in terms of my variable theta. Now the kind of tricky part will be how to relate dl and theta. But I know that L is equal to R times, or let me write it in a different way. I would rather reduce the number of variables, so I would rather express L in terms of my variable and some constant. D over L this is equal to tangent theta. Or L is equal to d over tangent theta. Do you agree? Well, then what is dl? As I change theta very slightly, what will be the change in the length L? Well, let's see. It's dl by d theta times d theta. You see, L depends only on theta. D is just a constant. So if I change theta very slightly by d theta, this is how much my dl will change. I have to take the derivative of L with respect to theta. Well, I always have a difficult time remembering what's the derivative of 1 over tangent theta. So let me take the longer way. So this will be d by d theta of d times cosine theta divided by sine theta. This is the definition of 1 over tangent. Don't get confused. This is that length d. Times d theta. Let me just change this to L to avoid confusion. Large L. Well, now we have this fraction. I can just take the derivative. So that will be L times d theta times the derivative of cosine is minus sine times the numerator minus the numerator times the derivative of the denominator divided by the denominator squared. This is the derivative of this fraction. Well, this is minus 1. And sine, this is just minus L d theta divided by sine squared theta. So this is the relation. dl is equal to minus L d theta divided by sine squared theta. This minus sign just tells me that as theta is increasing, L is decreasing. That is what that minus sign means. Well, that is kind of expected. If L is decreasing, as this length is getting smaller and smaller, theta will be increasing. So let's see, this is our dB. Or this is our B. This is equal to minus mu 0 I over 4 pi L. Instead of dl, I have the theta over sine squared theta. Minus L, I already took it out of the integral. Then I have 1 over r squared, but r is this one over here. R is given here, so 1 over r squared is nothing but sine squared theta over L. Sine squared theta over L times sine theta over L squared.
We can take out 1 over r squared.
This is 1 over r squared. This is from dl, and this is from the definition of dB. Well, taking the theta as our free variable was a wise choice, so now we have a simple integral over theta. So this cancels, so B is equal to minus mu 0 I over 4 pi the theta sine theta. Why? Well, it's just a notation, whichever one you like. If you want to write dl on this side, just do it. Now, what are the limits on theta? Zero to 180. Well, let's say 0 to 180. 0 to pi. So if it is from 0 to pi, minus mu 0 I over 4 pi L times, well, the integral of sine is minus cosine theta. Theta is equal to 0 to pi. Cosine of pi is minus 1 minus minus 1 is just 1. Cosine 0. So this is equal to minus mu 0 I over 2 pi L. Now you see, we sum over all the DL, starting from infinity up to over there. So when we have a very small segment right over there, this angle, and as we go down, that angle becomes smaller and smaller, so we go to 0. Then when we reach over here, it's 90 degrees. When we take this DL, it becomes larger than 90. So when we go to infinity, that angle becomes 180. But now there is a problem. We did something wrong. You see, before we began, we said that, okay, magnetic field is in the z direction, and this is the magnitude of the magnetic field. So it's positive. That is positive. We are just summing positive numbers. The magnetic field has to be in the z direction. So this B has to be a positive number. But you see, here it's a negative number. Now this part kind of gets tricky because you see the mistake we made. What are the limits on DL? So, okay, so let's say you are saying that we are integrating from minus infinity to plus infinity, right? But then the trick is, this DL should be a positive number. So you are increasing L from minus infinity to plus infinity, right? You see, this is the DL that we had defined over here. If DL is positive, L is decreasing. So that's kind of the tricky part. You see, what we defined as L. L was this length over here. Well, some of you were opposing, why do I have the reference point? It's like I took the positive L to be in that direction. Because this is a positive number, I said. So it's equivalent to saying this is the positive L direction. So my DL vector over there minus DL in the L hat direction. This is the L hat direction, in a sense. So there's that minus sign, which we ignored all the time. So that minus sign I will have over here. Now everything is positive. Well, it wasn't kind of a wise choice. I should have started with choosing the L to be the upward direction, choose this DL over here, then I wouldn't have this problem of the L, of the sign. But I mean, what we are doing is correct. So this is the total magnetic field at the end. B is mu 0 I over 2 pi L in the z direction. Let me first draw the magnetic field lines, and then I will have your question. So we said that this is our wire. This is I, and we said that here the magnetic field is pointing into the screen. Well, we could have just redo the calculation everywhere. We will see that at this point it is out of the screen. it comes out. At every point on the right, it will be into the screen. At every point on the left, it will be out of the screen, and it will just form such circles.
This is made by calculations, right?
Yes. Well, you see, this wire already has a symmetry around rotations over here. So if this is my wire, the magnetic field at this point is pointing in that direction. If I rotate the wire, this is the magnetic field direction. It's just rotating around my wire. It's enough for me to calculate only at this point. Then I already know that it's a circle. And if you look at it from the top, this is the current. These are how the magnetic field lines look like. So their intensity gets smaller as you go away from the wire because the magnitude gets smaller. And again, the direction you can determine by your right hand. This is the direction of the current. Point your thumb in the direction of the current or in the direction of the current. Then your fingers curl in the direction of the magnetic field lines. Now, questions?
First question I had two actually. The first one is, why did you make the upper limit pi? Shouldn't it be pi upon 2?
Why?
Because pi would mean that it's exactly as 90 degrees inverse, right?
No, pi over 2 is 90 degrees. Pi is 180.
Right, so it should be pi over 2 instead of pi. Because why did you make it complete? Why did you make it like this, 180 degrees?
Well, let's see. Theta is this angle. At infinity minus, at this point, this is the angle. So it's 0. Now, when I go up there, this point is right over here. It becomes 180.
But it would never be able to reach B if it goes above 90 degrees, right? If it goes above pi upon 2. Because
Why? So when I'm right at this point, then theta is 90 degrees. But if I take this point over here, the angle over here is larger than 90. If I take even a segment very, very far away, then that angle will approach 180.
And the second question is, when you just drew those lines, if you could just go down a little bit. On the right-hand side from the plot view, we can see the circles are getting larger, right?
Yes.
Is it because on the left-hand side, those circles are getting larger?
These ones?
Yeah, they're not getting larger, right, as you go down.
No. Well, you see, this wire has two symmetries. One is rotations around this axis, nothing changes. So basically, that tells us that once we evaluate the magnetic field at this point and seen that it is vertical, we know that the magnetic field lines have to be circle. We also know that this wire doesn't change if we just push it upward or downward. So the magnetic field here should be the same as the magnetic field here, should be the same as the magnetic field here.
So they overlap when you look at the top down, right? When you look in top down.
Yeah, from the top, I mean, at this direction, there are infinitely many of them. If you would draw more magnetic field lines over here, they will just look like this.
Okay.
Other questions? Yes. How? We will study that in a couple of chapters. Other questions? So see you tomorrow.